Hi everyone, here's a bonus topic. How do you factor cuties, quadratic trinomials, without guessing? That's something that you may have wanted to know back in your Algebra 1 class. Well, remember our old friend here, 4x cubed minus 5x squared minus 7x plus 2. In fact, we were able to factor that over z, the set of integers. Now, we used the rational zero test or rational roots theorem to find that 2 was a rational zero. So by the factor theorem, x minus 2 is a factor, and we could do synthetic division. We got this, that this equaled the factor x minus 2 times this quotient we got when we divided this by this. This QT was 4x squared plus 3x minus 1. And actually, a lot of students would have gotten stuck there. How do we factor that thing? How do we factor that? If you hate guessing, there's a way to do it without guessing. Because some students may not want to stare at this and try to figure it out from that. They might want to use what formula? Why don't we try using the QF, the quadratic formula? That should be able to help us. So let's apply the QF, the quadratic formula. Let's find the zeros first. They're potentially imaginary. In general, we're going to find the complex zeros. They could be imaginary. So when you find the zeros using the quadratic formula, you get 1/4 and -1, which means that by the factor theorem, x minus 1/4 will be one factor, and x plus 1 will be the other factor. Again, 1/4 is a 0, so x minus 1/4 better be a factor. -1 is a 0, so x plus 1 better be a factor. But now, don't forget, we have to rescale this so that we get the appropriate leading term here. The leading term here is not just x squared, it's 4x squared. You need the leading coefficient. This is like LFT form. It is LFT form. As it stands, this is LFT form. But wait, let's say we want to factor this over the integers. What if we want to factor this polynomial over z, the set of integers? Here's what we could do. We don't like the -1/4 because it's not an integer, but what could we do? We could take the 4 out here, the leading coefficient, and multiply it through this factor. We can distribute. And when we do that, what do we get? We get the factor 4x minus 1, which is a factor over the integers. So then we get that this QT factors as the factor 4x minus 1 times the factor x plus 1, or vice versa. Now, many people might say, well, wait a minute. I mean, if you found the zeros to begin with, don't we care about the zeros? Well, sometimes we do. Sometimes we ultimately want the zeros or the x-intercepts. But what if we wanted the actual factorization? Because let's say we have to simplify a rational expression like this. You would want to factor this QT, see what happens, and lo and behold, x plus 1 is a factor of the bottom of this QT. So you'd have to simplify, and you get 1 over 4x minus 1. So sometimes you do want to factor a QT for factoring's sake, or for the sake of simplifying. Also, another point I want to make. Let's say that your zeros aren't as nice. Let's say you get imaginary zeros, for example. Well, then you should be able to at least factor over c. We know that at the outset, we should be able to factor this over c using LFT form. We should be able to do that. And if these turn out to be ugly imaginary numbers, we know we can at least factor over c, the set of complex numbers. We know we can do that at this point. And remember, if you get a pair of complex conjugates here, then the corresponding factors would be x minus one of the complex conjugates. You'll probably need grouping symbols, times the factor x minus the other complex conjugate. Again, you'll probably need grouping symbols. And we have here a pair of CCs, a pair of complex conjugates. So the quadratic formula can be helpful, in part because you do sometimes get difficult imaginary zeros. But even if you could factor this over the integers and get rational zeros, you get rational zeros exactly when a guy like this factors over the integers, then you could use the QF anyway. Use the factor theorem, and then maybe bring in the leading coefficient appropriately in such a way that you get factors over z, the integers. And you can do this. So if you ever run into your algebra teacher on the street, your algebra teacher gives you this. If you know the quadratic formula and you know these tricks, you can produce something like this. Bear in mind, if you have something like this, where if you have a 6 on the outside, and let's say x plus 1/2 over here, and x minus 1/3 over here, let's say you got negative 1/2 and positive 1/3 as your zeros, then you have to be a bit more creative. Then you can split the 6 as 2 times 3. The 2 goes through here, the 3 goes through here. But you can get factors over z. So you can use the QF to factor cuties. You don't have to guess. You just have to be a little clever sometimes.